Hi, everyone. And yeah, thanks also from me for the invitation to Audrey on behalf of the EPOS MSL. I'm really pleased to talk about this. And like Giacomo before me, this is a nice surprise because this is also kind of not really what my main research is about. And it's something we did a while ago, but I'm always really excited to find someone who's interested to listen to me talk about it. So I'm going to talk about vitrified forts in the Iron Age across Europe. I'll tell you a bit about what those are in a moment, but I think this fits really nicely with today because this is really a meeting point for geoscience with archaeology through physical rock testing or rock mechanics and rock physics. And I should say, like Giacomo before me, I'm not an archaeologist, so I should apologize to archaeologists in the audience for any oversimplifications I make. I'm always learning more things about archaeology. So vitrified forts are these curious and weird forts throughout Europe. They're all over the place and they look a bit like this picture. This is an example of one from Aberdeenshire in Scotland. And they are enclosures, so walls that surround a central area where there were buildings in the Iron Age. And the walls always, they're called vitrified if they contain evidence for being partially melted at some point during the time that they were either built or occupied. So they're normal fort walls in all the normal respects, except they have evidence for being partially molten. They occur in the late Bronze Age and into the Iron Age in Europe, but there's none found in the Roman period. So once the Romans conquered Europe and moved through Europe, these types of forts stopped being found. And as I say, they're throughout Western and Northern Europe in particular. This is where they are found. And I should say that we don't know, this isn't an exhaustive list. We don't know where all of them are, but this is all the ones that have been found so far. So there are lots in Scotland. This is where they were first described, and it was identified that they were strange compared with other forts of the period. But beyond Scotland, there are some in Yorkshire in the UK here. So this is the Winkerbank example. There are some in Western Germany, in Northern France, and probably throughout France. But not much has been written about those. And there's some Bronze Age examples in northern Spain. There's also an amazing example in Sweden, in a place called Broborg. And this is one where if you Google Broborg, Sweden, you can see, if you put the satellite layer on Google Maps, you can see it immediately in the place that Google takes you to. So I'd encourage you to do that if you want to see an example. So yeah, they're not really in Eastern or Southern Europe, which I'll come back to that observation later. So important for this study, they're made from local stone, so rocks available to the local area around which they were built. They're made from a range of rubble and particle sizes, including lots of very small particles of stone between the larger blocks. They always have a really variable extent of fusing and melting. So this example here is a really good example of like a continuous molten fort, which is often used as the example that people show, but they're not always as nice as that. They're sometimes a bit less well melted all the way around. When you pick up pieces of the fort, they look a bit like this. So the main characteristic of the pieces of the fort that are preserved today are clasts, sometimes cracked clasts because of the temperatures that they were heated to, with a matrix between them of molten rock that has fused the clasts together. And that's what holds some of these blocks together. So when you cut them open, and these are some early examples where you see angular clasts in a matrix of glassy material or slightly crystallized material that was once glassy. When the examples I just showed you are all from forts that were built from metamorphic or igneous basement rocks that were available in those locations in Scotland. But at these locations further south in England, they're built from sandstone, and here the vitrification is less intense, it's less obvious, but it's still the case that these are clasts held together with a glassy matrix. And sometimes if the sandstone is layered with a mica-rich layer, then when they're partially melted, the micas can dehydrate and form bubbles. And that's quite common in these sandstone fort walls. So the key question here is how and why was this done? Why would you melt a wall in the Iron Age? And because this is these are societies before writing, we don't have anything to go on except the materials that they left behind. So we have to use the walls themselves to work out why this might have been done. And if you look up vitrified forts, you can see some really interesting theories that have been put forward. Some really early theories was that this must have been associated with volcanic activity. We don't think that's true because there wasn't extensive volcanic activity throughout Northern and Western Europe in the Iron Age. People have invoked lightning strikes or even aliens as the cause of these. But in the more serious academic literature, you can organize the theories into these general categories. So the most well-explored theory is that this must be to do with warfare, and therefore it's the people attacking a fort who set fire to the walls in order to destroy the fort during an attack. Another theory is that this was to do with the building of the fort itself, and therefore is an engineering process of some sort. This theory has been discredited early on, and I'll come back to that. And the third sort of less easy to test model is that this is something to do with the activities of the people who lived in the fort. This seems reasonable because this is the Iron Age after all, where people are smelting and forging metals. So they might have been accidentally melting the rocks of the walls of the fort. And then people have suggested that it could be to do with rituals or cultural practices. I'm going to not talk about ritual or cultural practices because we don't really have any evidence for those. I'm also not going to talk about accidental vitrification of the walls due to forging, because that doesn't really explain how forts like this one could be vitrified all the way around continuously, very systematically. So we're left with two theories, something to do with attack and something to do with engineering. The engineering hypothesis, or the constructional hypothesis, was dismissed in 1937 on the basis of an experiment that people did where they reproduced a wall and then set fire to it for several days and looked to see afterwards what the state of the wall was. Unfortunately, they used a strange selection of materials. They used fire-resistant bricks, which obviously weren't available in the Iron Age and are the least likely material to melt. They also used basalt, rubble. They used modern firewood, which burns at a lower temperature than old hardwoods. And they may have used some extra fuel, which isn't a good test of Iron Age technology. These sorts of tests were then repeated in 1986. This was actually broadcast on the television as well. And this time, Ian Ralston did it correctly. He used granites and gabbros and schists. He used an appropriate type of wood, but unfortunately he had problems with the weather and wasn't able to sustain the fire for very long. And so the temperatures were much, much lower than they probably could have been. So we felt like the constructional hypothesis deserved testing some more, because we thought both of those experiments that have been performed on large-scale reconstructions of walls haven't been a good test of the hypothesis. So we did two types of experiment. First, we took some sandstone and some granodiorite, and we cored them and we heated them up for different temperatures and different times. And then we measured the strength of those materials after exposure to high temperatures. And we also crushed the same materials into a powder of different sizes and loaded those into crucibles and exposed them to the same temperatures and times and measured the strength of those materials afterwards as well. This is sort of replicating the clasts in these walls, and this powder is replicating the material between the clasts that we think might be responsible for holding together the clasts after vitrification. What we found was that in both the sandstone and the granodiorite, so on the left is the sandstone experiments and on the right is the granodiorite experiments, we found that the intact rock got weaker with exposure to high temperature in general. And in the case of the sandstone, it got a bit stronger again before getting weaker at even higher temperatures. And in the case of the powder or aggregate of rock material, that had no appreciable strength up until a certain point, and then it got very, very strong very quickly. The decrease in strength of the intact rock we attribute to microcracks, with the extra feature of the sandstone that the alpha beta transition of quartz plays a role in driving that microcracking. And in the sandstone, this strength increase appears to be due to slight partial melting holding the clasts of the sandstone together again. The granodiorite just gets weaker. But I'd like to focus on what the powdered rock does, which in both cases gets stronger. The reason we think the powdered rock gets stronger when it starts to partially melt is to do with a process called sintering, which involves the rapid reduction of porosity as the clasts in the powdered partially molten rock start to fuse together. Here is an example of a sintering process from left to right with time at high temperature. And you can see that at the end, the porosity, which is in black between the particles, has almost completely been destroyed, which increases the bulk strength substantially. We think this is a reasonable conceptual model for what's happening in these rocks, that the sintering is occurring in the small clasts between larger clasts, and therefore holding the material together and increasing the bulk aggregate material strength. A key question then is, how hot were these walls? So we did some in situ XRD measurements. This is an example from the sandstone vitrified wall, where we were tracking the decrease in the quartz peak in higher and higher temperatures, and the appearance of a cristobalite peak that replaces the quartz. Cristobalite is a high temperature polymorph of SiO2, so as quartz starts to break down, cristobalite forms, and that's tracking the partial melting. Similarly, we see the feldspar peak disappear almost at lower temperatures and is gone by high temperatures. We know the relative quartz abundance of the material from the walls themselves, and so we can compare our experiments with the wall material. And so this points to equivalent temperatures between 1100 and 1200 degrees Celsius, which is the kinds of temperatures that sustained hardwood fires can get to. So back to this diagram, this is in Kelvin. Sorry for mixing my units, but you can see that the sandstone sintered aggregate, the temperatures of the fire are lower than the sintering process that would increase the strength. Whereas for the granodiorite, these temperatures where the strength increases so much are almost exactly the temperatures that we think these walls got to. So in the case of granodiorite, we think strengthening can happen really easily. And in the case of the sandstone, it would have had to be hotter than probably was possible. So we have a rock type control or a lithology control on our vitrification potential. So with that information, we looked at what these forts are made from in Scotland, and we compared it with the basement rocks. And if you look around, almost all of the forts are made from igneous or metamorphic rocks, which have a lower solidus and therefore will start partial melting at lower temperatures. Whereas the one or two forts that are made from sedimentary basement rocks, those also happen to be the forts that are less well vitrified in general. So that's a good test for our hypothesis that this might have been deliberate, but a technology that was deliberate but less successful when sedimentary rocks were used as the fort material. As you look through Europe, in places like Sweden and northwest Scotland, there is more igneous and metamorphic basement than in Central Europe in general. Of course, that's a generalization, but it could be true, we think, that the technology starts in Northern Europe, where this would be most successful, this vitrification technology with these appropriate basement rocks. And then as the technology is communicated further and further south, it becomes less successful. And of course, the Iron Age people presumably didn't know much about the basement geology, and they just used the rocks near to them. So they might have been confused why this technology wasn't working. But at a similar time, as Roman mortar technology is moving northwards from where it was developed in Italy, this would quickly replace the vitrification technique. And so that might explain why we have a general time evolution of vitrified forts from Northwest Europe through to Central Europe. And then that time progression stops at almost exactly the time that the Roman Empire advances through Europe and the Iron Age comes to an end. So to return to our...
sorry, Fabian, for telling that we are running out of time.
Yes,
Very
yes.
sorry for this.
Yeah, no problem. I just wanted to conclude by saying that we've tested the engineering hypothesis, and we think that it shouldn't be dismissed as quickly as it has been. Thanks very much.